Hello friends, it is a database management system assignment 7 of an NPTEL course which is conducted in March 2020. Question number 1. Let TI be a transaction that transfers rupees 100 from account X to account Y. This can be defined as follows. These are the operations are given. Identify the correct statement related to the above transaction execution. Option A given, the database must be always consistent just after third step but before the fifth step. After third and before fifth step. Now see what is the value of X and Y. Say assume the value of X is 200, value of Y is 300. For this situation, for the ensuring consistency, we take sum of the balances for understanding the consistency. And consistency says before and after the transaction, the database system should be in a correct state. Here I have added some of these accounts and this will be used as a consistency requirement for this case. Now what is the sum of the balances? That is 200 plus 300, 500. Okay. Now what is the option given after third step but before fifth step? See, it is executed three steps. It means first read X, it is 200, minus 100 makes the value of X is 100. Then write this 100 back to the X, that is 100. Now next operation is read Y, 300. So now what is the possibility here? The sum of these two balances, 100 plus 300, 400. According to consistency requirement, this sum of these two balances should always be same before the transaction and after the transaction. But after step 4, before step 5, what is the sum of these two balances? 100 plus 300, 400, which is inconsistent state. But can we say this is inconsistency state always? No. Why? Because after step 4, it may execute step 5, 6 also. Suppose if it is executed 5 and 6. Now Y will be changed from 300 to 400 because 100 is added. Then finally it is performing write 400. So after it writes 400, now what is the sum of these two balances? What are the sum of these two balances? Which is 500. Now 500 after the transaction is correct because it is satisfying the consistency requirement. So that what we say, after step 3 but before step 5, the state of the system is 400, sum of the balance is 400. So that this 400 we can call temporarily inconsistent but not inconsistent always. Why? Because after execution of step 6, it is a consistent state. So option A is incorrect. Why? Because it is given always consistent. It is not always consistent. Option B says the database may be temporarily inconsistent. It is perfectly correct. So that option C and D also wrong statements. Question number 2. Consider the following schedule S of transactions 1, 2, 3, 4. These are the transactions given. Find out whether the following statements are true or false for the given schedule. Now look at, to find the conflict serializability, recoverability and cascadeless schedule, I suggest it is better to draw the schedule given for these 4 transactions, T1, T2, T3 and T4. Now T2 read X, T3 write X, T3 committed, T1 write X, T1 committed, T2 write Y, T2 read Z, T2 commit, T4 read X, T4 read Y and T4 commit operation. For testing conflict serializability, we should draw a precedence graph. For constructing a precedence graph, we have to draw 1 vertices for each of the transactions. Because we have 4 transactions, we have to draw 4 vertices and 1 vertices for each of the transactions. And each conflict operations we have to draw one edge. Now look Read X, write X is a conflict operation. What are the conflict operations? Read write, write read, and write write conflicts. Now T2 read X and T3 write X is a conflict from 2 to 3. So we have to draw an edge from 2 to 3. Next, this read X also conflict with write X. So that conflict is from 2 to 1. So draw an edge from 2 to 1. And check for the possibility of conflicts with operations of other transactions simultaneously. Now check write X. After write X we have a commit, because once transaction commits, it is no longer going to conflict with operations of any other transactions. So there will be no conflicts. This write X, after this write X we have a commit, because once committed it is no longer conflict with operations of other transactions. Now write Y, after commit only these are the operations. So this write Y is also no longer conflicts. Similarly read Z, read X, read Y, no conflicts at all. So that the precedence graph do not have any cycles, because no cycles, then schedule is conflict serializable. So first statement is true statement. Then second statement, recoverability. The recoverability and cascading rollbacks we decide based on the dirty read operation. Based on the dirty read operation. Here understand what is dirty read. Suppose some transaction I performing a write on some data X. This write is read by some transaction J. Same X is read by some transaction J. When before this I commits, if it is reading, this read is called uncommitted read, also called dirty read. Now observe, do we have any such dirty reads in the given schedule? After write X, it is commit only there, no dirty read. After the write X, no reads are there. After write X, no reads is there, but it is after commit only. So there will be no dirty reads. And because no dirty reads, keep in mind as a shortcut point, because no dirty read, we can say the schedule is recoverable. It does mean that J is not depending on I, because if a dirty read is there, we can say J depending on updated value of I. Such a dependency we don't have in this schedule given, because no dependencies. If any transaction is failed, we have to roll back only that transaction, no other transactions, so that recovery is always possible. Because you are rolling back only one transaction which is failed, not other transaction, means no cascading rollbacks. Because no cascading rollbacks, we can say schedule is cascadeless. So all three are true. So answer for this question is option C. Question number 3. Consider the following schedule. This is a schedule given. Question is, identify the number of view equivalent serial schedules. Number of view equivalent serial schedules. Here observe the transaction 1, 2, 3, 4 are reading X and 1, 2, 3, 4 are writing Y, because read X, write Y. And here, because all are read X, there is no conflicts. All are write Y. Here write writes are conflicts, but all these writes are in the sequential order. So the schedule is view serializable, we can say. The schedule is view serializable and schedule is conflict serializable. But question is, identify the number of view equivalent serial schedules. For view serializability, it is to satisfy 3 rules. That is called first read, last write, and write reads. Observe in the given schedule, we don't have any write reads. And first reads are there, all are first reads only. Means it is possible to become all be the first. Okay. And last writes, but among all writes, only this T4 is the last write. Okay. Only T4 is the last write. Because T4 is the last write, T4 should come in last position in the order of serializability. And this 1, 2, 3, these 3 writes can appear in any number of ways. Means T1, T2, T3 can appear in any number of ways. With 3 transactions, T1, T2, T3, how many possible serial schedules possible? 3 factorial. it does mean that totally 3 factorial equals 6 possibilities. After these 6 possibilities, for each of these 6 possibilities, last transaction should be T4 to satisfy the last write operation. So the number of view equivalent serial schedules are equals to 6. That is option D. Which of the following is not a goal of concurrent execution of the transactions? Not a goal, not a goal. Keep in mind, not a goal. Option A says improved throughput, improved resource utilization, reduced waiting time, reduced probability of deadlock. Actually, the concurrent executions are required for improving the throughput, resource utilization, and reduced waiting time. But this concurrent execution not have a goal of reducing the probability of deadlock. So option D is incorrect. Actually, if two transactions are running concurrently, suppose some transaction performing read operation and some transactions performing read and write operations, we call IO operations, and some transactions may perform CPU operations like A plus 100. Now observe here, this read A is called IO operation, A equal to A plus 100 is CPU operation. Suppose transaction 2 T1 performing CPU operation, then at the same time, instead of wasting the T2 to sit idle, the T2 can perform IO operation because it uses IO resources. Whenever T1 performs IO operation, now CPU resource is free. Now T2 should perform CPU operation and vice versa. So if you execute like this, it means you are allowing more than one transactions to run simultaneously, which improves the throughput, and resources will be utilized efficiently. Why? Because when we are using CPU, IO is utilized properly. When you are using IO, CPU is utilizing properly by other transactions. And waiting time of transaction also to be reduced. Suppose you make this T2 to start after T1, then T2 will start after the 3 operations of T1. But because you are allowing, when T1 is performing CPU, you are allowing T2 to perform IO operation. So obviously the waiting time of T2 is reduced. Because question is not a goal, A, B, C are the goals. Because question is not a goal, option D is the correct answer. Question number 5. Identify the correct mechanism to ensure durability property of a set of transactions. Durability is ensured by recovery management system of a database system. So answer is option A. And concurrency control, it is a responsibility of isolation property. And security management, query optimization techniques are not there. So answer is option A. Question number 6. Consider the following schedule. The schedule is given. Question is, choose the correct options for the above schedule. Here options are given. The schedule is a recoverable schedule, cascadeless schedule, recoverable, cascadeless. To verify recoverability and cascadeless, we need to identify, is the schedule do have any dirty read operation. Now what is dirty read? Suppose some transaction I performing write operation on some data X, that write is read by some transaction J when before commits. If this read is possible before commit. If it is reading before commit, this read is called uncommitted reads, or we also call dirty read. It does mean that J is depending on the updated value of I. We call it is there is some dependency. If dependency is there, we have to think about it, the recoverability and cascading rollbacks. Check, do we have any dirty reads in the given schedule? Here you observe a point. The T1 is performing write X and T2 is reading that value. Means 2 is depending on the value updated by 1. And because 2 is committed first before 1 commits, there is a possibility of non-recoverability. Why? Because suppose if T1 fails after T2 commits, after 2 commits, if one failed, this results T1 to be rolled back because based on the updated value of T1, T2 is executing. So that because 2 depending on 1, rollback of 1 requires rollback of 2, but rollback of 2 is not possible. Why? Because it is already committed. So means we cannot roll back. Because we cannot roll back, this schedule is said to be not recoverable. We call non-recoverable schedule. Non-recoverable schedule means this schedule had a problem with non-recoverability. Suppose if there is a failure occurs after read operation but before commit operation, if a failure occurs, we have to roll back T1, but rollback of T1 makes the rollback of T2 T2. Why? Because the execution of 2 depending on 1, because 1 failed before 2 commits, rollback of 1 requires both rollback of 1 as well as 2. Means it also had a problem of cascading rollbacks. It had a problem of cascading rollbacks. So means the given schedule had 2 problems. One is non-recoverability and cascading rollbacks. So option A given, the schedule is only recoverable, incorrect. The option B given, the schedule is only cascadeless, it is incorrect because cascading rollbacks are also possible on the given schedule. Option C given, the schedule is recoverable, it is incorrect. Why? Because it is non-recoverability. So option D is the schedule is neither recoverable, yes, nor cascadeless, yes. So answer for question number 6 is option D. Question number 7. Identify the correct options which are used in transaction control language. In database languages, there are various classifications, and one of the classifications is transaction control language. In transaction control language, there are some SQL statements comes under TCL or save point. We call save point, and we call rollback and commit. This comes under TCL. Here you see option A given save point, option D given rollback, and insert and update means inserting data, updating data. Because insert and update dealing with data in the database means these two comes under one of the classifications of database language called data manipulation language. Because question is used in TCL, transaction control language. What are used in transaction control language? Save point and rollback. So answer for the question is both option A and option D. Question number 8. Consider the following schedule. The schedule is having 3 transactions. Now question is choose the correct option for the above transaction schedule. Here the options are about view serializability and conflict serializability. For testing serializability, first we check for CS. Why? Because if a schedule is CS, it definitely be VS. Checking CS, we have an algorithm that is called precedence graph method, where each transaction denoted with 1 vertices and each edge corresponding to a conflict operation we have to draw. What were the conflict operations? Read write, write read, and write write operations on same data by different transactions. Observe carefully what are the conflict operations. For each of the conflict operation you have to draw an edge between the transactions. Now read X of T1 conflict with write X means it is a conflict from 1 to 3. Write Y, write Z, no more conflicts. This write X, check write X of T3 with T2 and T1 operations because these are Y and Z, no conflicts. Again write Y, this is conflict with write Y means it is a conflict from 3 to 2. So draw an edge from 3 to 2 and no more conflicts. Write Y, These are the Z's, no conflicts. This is read Z, conflict with write Z. It is a conflict from 1 to 3. Because edge is already there from 1 to 3, you need not to draw one more edge. And this is write Z, this is write Z. Now it is a conflict from 3 to 2. This edge is also already present. Now this is a resultant graph. Because the resultant graph do not have any cycles, we can say the schedule is conflict serializable. And we know that every conflict serializable schedule is also view serializable schedule. So the schedule is both conflict serializable and view serializable. That is matching with an option C. What it is given? The schedule is both view serializable schedule and conflict serializable schedule. So answer for question number 8 is option C. Question number 9. Consider the following schedule S of transactions T1, T2, T3. These are the operations are given. Identify the number of conflict equivalent serial schedules of S. Now observe what transactions are given T1, T2, T3. First, I would like to draw the schedule in a neat way. T1 is having read X, write Y operations. Now T2 read X, write Y operations. Now T3 write X, write Y operations. These are the order. But observe friends, here it is given in the serial order, right? Because it is given in the serial order, so that the number of conflict equivalent schedules are possible equal to 1. And in another way, if we draw a precedence graph for the given schedule T1, T2, T3, here you observe read X is conflict with write X. This is a conflict that is from 1 to 3. And read X also conflict with write X, that is from 2 to 3. And write Y conflict with write Y, 1 to 2 and 1 to 3, that is 1 to 2 and 1 to 3 already there. This write Y conflict with write Y, that is from 2 to 3. And any more edges? No more. If you perform a topological sort, so we have to start with in degree 0, that is T1 first. After we remove T1 along with outgoing edges, next vertices with in degree 0 is T2 and T2 removed along with outgoing edge. Last vertices is T3. So the order of serializability is T1, T2, T3. So it is equivalent to how many conflict serializable schedules? 1. So answer for the question 9 is option A. Question number 10. Identify the correct option for the following precedence graph corresponding to a schedule. Here, observe the precedence graph. If a precedence graph is given, first we have to look for the cycles. Do we have any cycles in the graph? Observe carefully. T4 to T1, T1 to T2, T2 to T3, T3 to T4. So here we have a cycle. Because cycle is there, it is not conflict serializable. And because cycle is there, there is a possibility of deadlock. Then the answer for question number 10 is there will be a deadlock situation in the schedule. And here, because cycle is there, not conflict serializable, because schedule is not given, we cannot decide about view serializability. So that option C is also wrong. So what we can conclude, because cycle is there, it is possibility to have a deadlock. It means that 4, 1, 2, 3 may wait for one another in a circular way, causes a deadlock situation. So answer for question number 10 is option D. Thanks for watching. Please like, share and subscribe.